The Kraken galaxy and the violent history written in stars. Look up at the Milky Way on a clear night. Those stars you see, they're not all native to our galaxy. Some are invaders, prisoners of war from cosmic battles that happened billions of years ago. And one of the most spectacular discoveries of this hidden history is a galaxy we call Kraken, a massive ghost that our Milky Way devoured long before the first fish swam in Earth's oceans. In 2019, astronomers did something remarkable. They predicted the existence of a galaxy that had been dead for over 9 billion years. Not by observing it directly, because it no longer exists as a distinct object, but by running the cosmic clock backward through computer simulations. The models suggested that our Milky Way, this seemingly peaceful spiral we call home, had once been a cannibal. And Kraken was its largest meal. The prediction was bold. If Kraken existed, it would have been the most massive galaxy ever consumed by the Milky Way relative to our galaxy's size at the time of the merger. We're talking about a collision between two galactic titans when our galaxy was still young and growing. But here's the fascinating part, for independent research teams later found the evidence. The forensic traces of this ancient murder were hiding in plain sight, scattered across our night sky. To understand how we found a galaxy that died billions of years ago, we need to talk about galactic archaeology. This field is revolutionizing our understanding of cosmic history, and it works surprisingly like detective work at a crime scene. When galaxies collide and merge, they don't simply blend together like watercolors. The physics is far more complex and beautiful. Stars from the consumed galaxy get scattered into new orbits, but they retain chemical fingerprints and orbital patterns that betray their origin. It's like finding fragments of different pottery styles in archaeological layers. Each piece tells you about a different civilization that once existed. The Milky Way is actually a graveyard. Current estimates suggest our galaxy has consumed somewhere between dozens to hundreds of smaller galaxies throughout its history. Each one left traces. Some left streams of stars trailing through space like cosmic breadcrumbs. Others contributed to the stellar halo, that diffuse cloud of ancient stars surrounding our galactic disk. But most of these victims were relatively small, dwarf galaxies with masses just a fraction of the Milky Way's bulk. Kraken was different. The simulations suggested it had been massive, possibly containing as much as 30% of the Milky Way's total mass at the time they collided. Imagine two cities merging, but one of them contributes nearly a third of the total population. That's not a snack, that's a full merger event that would have fundamentally reshaped the structure of our galaxy. The evidence came from studying globular clusters and ancient stars with unusual chemical compositions. Globular clusters are dense spherical collections of hundreds of thousands of stars, all born around the same time. The Milky Way has about 150 of them orbiting in the halo, and they're incredibly old. Some formed over 13 billion years ago, less than a billion years after the Big Bang itself. These clusters are useful because they're like time capsules. Their stars all formed from the same primordial gas cloud, so they share chemical signatures. And crucially, when a galaxy gets consumed, its globular clusters get inherited by the cannibal galaxy but retain their original orbital properties. Researchers analyzing the orbits and chemical compositions of globular clusters noticed something peculiar. A substantial group of them shared similar orbital characteristics and chemical abundances that didn't quite match the rest of the Milky Way's population. They were moving in eccentric, highly inclined orbits, exactly what you'd expect from debris of a major merger. The chemistry was off too, suggesting these stars formed in a different environment than the bulk of Milky Way stars. When you plot the orbits of these clusters and trace them backward through time using gravitational simulations, they converge. About 9 billion years ago, these clusters were all part of something else, something that no longer exists as a coherent structure. The researchers needed a name for this ghost galaxy, and given its massive size and the way it was torn apart, they chose Kraken, named after the legendary sea monster from Scandinavian folklore. But here's where it gets truly interesting. The discovery of Kraken rewrites part of our galaxy's biography. Before these findings, the Gaia-Enceladus merger was thought to be the most significant collision in Milky Way history. Gaia-Enceladus was another large galaxy that merged with the Milky Way about 10 billion years ago, and its discovery in 2018 was already considered groundbreaking. That merger dumped enormous amounts of stars into our galactic halo and probably triggered intense star formation. Kraken appears to have been even larger than Gaia-Enceladus, making it the heavyweight champion of Milky Way mergers. The timing is remarkable too. These two massive collisions happened relatively close together in cosmic time, during a particularly violent period in our galaxy's adolescence. It's like discovering your peaceful hometown was actually the site of multiple major battles during its founding years. The implications extend beyond just knowing our galaxy's history. These mergers fundamentally shaped the structure we see today. When massive galaxies collide, the gravitational interactions don't just redistribute stars, they trigger bursts of new star formation. The gas clouds in both galaxies get compressed by shock waves, causing them to collapse and form new stars at accelerated rates. Some of the stars in our night sky, possibly even some near our Sun, might owe their existence to the violence of the Kraken merger. There's also the dark matter component. Galaxies aren't just made of visible stars and gas. Most of their mass is dark matter, that mysterious substance that doesn't interact with light but exerts gravitational force. When Kraken merged with the Milky Way, it brought its dark matter halo along. That dark matter is still here, threaded throughout our galaxy, contributing to the gravitational scaffolding that holds everything together. We can't see it directly, but its gravitational effects are measurable. Some researchers are now investigating whether specific features in the Milky Way's dark matter distribution might be remnants of the Kraken merger. The detection methods deserve attention because they represent a triumph of modern astronomy. The Gaia Space Telescope, launched by the European Space Agency, has been measuring the positions and velocities of over 1 billion stars with unprecedented precision. Before Gaia, we could measure stellar motions, but not with enough accuracy to trace the detailed orbital histories of individual stars over billions of years. Gaia changed that. It's creating a three-dimensional map of stellar motion so precise that we can essentially watch galactic archaeology in action. Combined with spectroscopic surveys that measure stellar chemical compositions, we now have both the where and the what for millions of stars. This is how the 4 independent research teams could all arrive at similar conclusions about Kraken's existence. The data was clear enough that multiple groups analyzing it from different angles saw the same ghost. But let's zoom out and consider what this tells us about galaxy formation in general. For decades, astronomers debated 2 competing models. The top-down model suggested galaxies formed as single, coherent structures that gradually evolved. The bottom-up model proposed that large galaxies like the Milky Way assembled through the gradual accumulation and merging of smaller galaxies over billions of years. The evidence from Kraken and other merger remnants strongly supports the bottom-up scenario. Our galaxy isn't a pristine original creation, it's a composite, assembled from dozens or hundreds of smaller building blocks. This hierarchical assembly process is actually a prediction of our standard cosmological model, lambda CDM, which describes the universe's evolution since the Big Bang. In the early universe, tiny density fluctuations in the distribution of matter got amplified by gravity over time. Small clumps of dark matter attracted normal matter, forming the first small galaxies. These then merged to form larger galaxies, which merged to form even larger ones, creating a cosmic hierarchy. The Milky Way sits somewhere in the middle of this hierarchy, big enough to have consumed many smaller galaxies, but small enough to be eventually consumed itself when we inevitably collide with Andromeda in about 4 billion years. That future collision with Andromeda, by the way, will be an even more spectacular event than the Kraken merger. Andromeda is actually slightly more massive than the Milky Way, so this will be a merger of peers rather than a one-sided consumption. The result will be a giant elliptical galaxy that astronomers have already nicknamed Milkomeda. Stars from both galaxies will get thoroughly mixed, creating new orbital patterns. Some will be flung into intergalactic space, becoming orphan stars wandering the cosmic void. The supermassive black holes at the centers of both galaxies will spiral together and eventually merge, releasing gravitational waves so powerful they'll ripple across the universe. But back to Kraken and the ancient past. One fascinating aspect is what this means for the habitability history of our galaxy. Galactic mergers are violent, chaotic events. The gravitational perturbations can send stars careening into new orbits, including potentially pushing them toward the galactic center where radiation levels are dangerously high for life. Nearby supernovae become more common during periods of intense star formation, and a close supernova could sterilize a planet by stripping away its atmosphere with high-energy radiation. However, mergers also distribute metals, elements heavier than hydrogen and helium, throughout the galaxy. These metals are created inside stars and released when they die. Rocky planets like Earth require these heavier elements to form. The violence of mergers might actually help spread the ingredients for planet formation more evenly through the galaxy. So while the Kraken merger might have been destructive in some ways, it also could have enriched regions of the galaxy with the raw materials needed to build solar systems like ours. There's a philosophical dimension worth considering. Every atom in your body heavier than hydrogen was created inside a star. This is the famous, "we are star stuff" realization that Carl Sagan popularized. But we can be even more specific now. Some of those atoms were almost certainly created in stars that belonged to Kraken. You are made partly from the remains of a galaxy that died before our solar system even existed. The iron in your blood, the calcium in your bones, the oxygen you breathe, these elements cycled through multiple generations of stars, some of which spent their lives in a completely different galaxy before it was violently absorbed into ours. The ongoing research into Kraken and similar merger remnants is revealing more complexity than anyone expected. It turns out there were multiple significant mergers, not just one or two. Names are being assigned to these ghost galaxies as they're identified: Sagittarius, discovered earlier and still in the process of being consumed; Gaia Enceladus, the massive merger contemporary with Kraken; Sequoia, another large progenitor, and several smaller ones. Each contributed stars, gas, dark matter, and dynamical energy to the Milky Way's evolution. The challenge now is disentangling all these overlapping events. Imagine trying to reconstruct a building's construction history when multiple different architecture firms contributed at different times, using different materials, but all the records were lost and you only have the finished building to examine. That's essentially what galactic archaeologists are doing. They're using the distributions of stellar ages, chemical compositions, and orbits to separate the different merger events and understand their individual contributions. Machine learning is becoming increasingly important in this work. With datasets containing information on millions of stars, humans can't possibly analyze all the patterns manually. Algorithms can identify clusters of stars with similar properties, trace orbital histories, and even predict where to look for additional evidence of specific merger events. The discovery of Kraken was aided by these computational techniques, which could process the massive datasets from Gaia and spectroscopic surveys to identify the coherent group of stars and clusters that once belonged to this ancient galaxy. There's also the question of what happened to Kraken's central supermassive black hole. Most galaxies, including dwarf galaxies, have supermassive black holes at their centers. When galaxies merge, these black holes usually migrate toward the center of the merged system and either settle into orbit around each other or eventually merge themselves. The Milky Way's central black hole, Sagittarius A-, has a mass of about 4 million times the Sun. Did Kraken's black hole merge with the progenitor of Sagittarius A-? Is it still wandering somewhere in the galactic halo? Or did it somehow get ejected from the system entirely through a gravitational slingshot effect? These questions remain open, and searching for wandering supermassive black holes in the Milky Way is an active area of research. The technology enabling these discoveries is advancing rapidly. The next generation of extremely large telescopes coming online in the next few years will be able to study individual stars in the Milky Way's halo with unprecedented detail. Spectroscopic surveys will measure chemical abundances for tens of millions of stars, not just the current samples of hundreds of thousands. Space-based missions beyond Gaia are being planned to measure stellar positions and motions even more precisely. Future gravitational wave detectors might even be able to detect the ancient merger of supermassive black holes from events like the Kraken merger, if we can develop sensitive enough instruments. Gravitational waves travel at the speed of light, so the waves from the Kraken Milky Way merger have long since passed through our region of space, but next-generation detectors like LISA might catch similar events happening in distant galaxies, giving us real-time observations of what the Kraken merger might have looked like. There's something profound about being able to reconstruct events that happened billions of years before Earth even existed. The universe has no memory in the traditional sense. There's no cosmic record book keeping track of everything that happens. But physics provides a kind of memory. The laws of gravity and motion ensure that ancient events leave traces in the present distribution of matter and energy. Those traces can be read by anyone clever enough to know what to look for. The Kraken discovery also reminds us how much we still don't know about our own galactic neighborhood. The Milky Way seemed like familiar territory. We've been studying it for centuries. Yet we're still finding evidence of massive structures and events we never knew existed. If our own galaxy holds such surprises, imagine what we might discover when we can study other galaxies with similar detail. Some galaxies have experienced even more dramatic merger histories than the Milky Way. Elliptical galaxies, those smooth, featureless blobs of stars, are thought to be the product of major mergers between spiral galaxies. When two spirals collide, their delicate disk structures get completely disrupted, and the result is an elliptical galaxy with stars moving in random orbits rather than the organized rotation of a spiral. The Milky Way has been fortunate. It's had many minor mergers and a few major ones, but nothing so catastrophic as to destroy its spiral structure entirely. The rate of galaxy mergers has decreased over cosmic time. In the early universe, when galaxies were closer together and the universe was smaller, mergers were far more common. We can observe this by looking at distant galaxies whose light has taken billions of years to reach us. We're seeing them as they were in the past. These early galaxies are messier, more irregular, and more frequently colliding than nearby galaxies we observe in the present day. The Kraken merger happened during this more violent epoch when the universe was younger and galactic collisions were routine. This raises an interesting question about the conditions for life. If major mergers were common in the early universe, and if they create hazardous conditions for life through increased radiation and gravitational disruption, then perhaps there was a minimum age the universe needed to reach before galaxies could settle down enough for complex life to evolve. The Kraken merger happened about 9 billion years ago. The solar system formed about 4.6 billion years ago, roughly 4 to 5 billion years after the Kraken merger. Perhaps that time gap was necessary for the Milky Way to settle down after its violent youth and create the stable conditions needed for something like our solar system to form and persist. Of course, this is speculative. We don't know how sensitive life's emergence is to galactic conditions. Maybe life is remarkably resilient and can arise even in dynamically active galaxies. Maybe it's incredibly fragile and requires billions of years of galactic stability. We have exactly one example of life, on Earth, so generalizing is difficult. But the discovery of events like the Kraken merger adds another variable to consider when thinking about the cosmic conditions necessary for life. The naming of these ghost galaxies is interesting in itself. Astronomers have chosen names from mythology and legend: Kraken, Sagittarius, Gaia Enceladus, Sequoia. There's something fitting about naming these ancient, destroyed galaxies after mythological creatures and legendary beings. They existed in a time before planets, before stars like our Sun, in an era we can only access through forensic reconstruction. They're as distant and legendary to us as any ancient myth, yet we can study their remains with precision. Each of these mergers probably had its own character and consequences. Kraken, being so massive, likely delivered a huge amount of dark matter to the Milky Way and triggered extensive star formation. Gaia Enceladus, merging around the same time, added its own contribution. Smaller mergers contributed less dramatically but still left their mark. Together, they created the complex, layered structure we observe today, a galaxy that is less like a single entity and more like an ecosystem built from many different components. The stars we see at night are survivors of these cosmic upheavals. They formed in different galaxies, were scattered by gravitational chaos, settled into new orbits, and now shine down on us as if they'd always been part of the Milky Way. Some of them might have witnessed the merger itself, they're old enough. Red dwarf stars can live for trillions of years, so some of the faint red dwarfs in our galaxy could have formed in Kraken when it was still an independent galaxy, witnessed the collision and merger, and will continue existing long after our Sun dies. There's a detective story quality to all of this that makes it particularly compelling. Astronomers are assembling a picture of events that happened eons ago using only subtle clues in the present. It's like reconstructing an ancient battle using only the artifacts left buried in the ground, except the battlefield is hundreds of thousands of light years across and the battle happened when the universe was less than a third of its current age. The computational simulations that predicted Kraken's existence are themselves remarkable achievements. These simulations model the evolution of dark matter structures and galaxy formation from the early universe to the present. They incorporate gravity, gas dynamics, star formation, supernova feedback, black hole growth, and numerous other physical processes. Running these simulations requires some of the world's most powerful supercomputers, processing the interactions of millions or billions of simulated particles over billions of years of cosmic time. The fact that these simulations predicted Kraken before it was observationally confirmed is a powerful validation of our theoretical understanding of galaxy formation. It suggests we really do understand the fundamental processes, even if many details remain uncertain. When theory predicts something and observation confirms it, that's science working exactly as it should. But there are still surprises. Not everything matches predictions perfectly. Some aspects of galaxy formation remain puzzling, like the distribution of satellite galaxies around the Milky Way or the internal structures of dark matter halos. These tensions between theory and observation are where new discoveries happen, where our understanding gets refined and expanded. The Kraken story is ultimately about perspective and time. From a human perspective, the Milky Way seems eternal and unchanging. The constellations our ancestors saw are essentially the same ones we see today. But on cosmic timescales, everything is dynamic. Galaxies collide, merge, transform. Stars are born and die. The very structure of space is expanding, carrying distant galaxies away from us. Nothing is permanent except change itself. 9 billion years is an incomprehensible span of time for humans. Our species has existed for perhaps 300,000 years, a blink on cosmic scales. All of recorded human history covers maybe 5,000 years. 9 billion years ago, Earth didn't exist. The Sun didn't exist. The solar system's region of the galaxy might have been part of a completely different structure, possibly part of Kraken itself before it was destroyed. Yet we can study this deep history. We can reconstruct events that happened before our planet existed. We can identify stars that belong to other galaxies and trace their journeys across billions of years. This ability to transcend our brief existence and understand cosmic timescales is one of humanity's greatest intellectual achievements. The work continues. New data arrives constantly from Gaia and other surveys. Simulations become more sophisticated. Machine learning algorithms get better at finding patterns. Each year brings new insights into the Milky Way's merger history and the fates of galaxies like Kraken. We'll probably discover more ghost galaxies hiding in our stellar census, each adding another chapter to our galaxy's biography. Perhaps one day, astronomers in the far future, possibly not even human, will study the Milky Way-Andromeda merger the same way we study Kraken today. They'll identify groups of stars with unusual orbits and chemical signatures, trace them back to their origins, and piece together the story of how two galaxies collided and merged to create the galaxy they inhabit. They'll give our galaxy a name, classify its contribution to the merger, and add it to their catalog of ancient ghosts. In this way, the cosmic story continues, each era's catastrophe becoming the next era's archaeological puzzle. The Milky Way is not the galaxy we thought it was. It's not a pristine spiral that's existed unchanged since the early universe. It's a composite, a patchwork, a survivor that built itself through violence and consumption. Kraken is just one of many victims, but its size and the dramatic nature of its discovery make it a particularly vivid illustration of this hidden history. Every time you look at the night sky now, you can know that among those stars are the scattered remains of a galaxy that died before our world began, its pieces now woven into the structure we call home. The discovery of Kraken opens deeper questions about what we're not seeing. If 4 independent teams could identify such a massive merger only recently, despite having studied the Milky Way for centuries, what else are we missing? The galaxy contains roughly 200 to 400 billion stars, and we've cataloged detailed information for only a tiny fraction of them. Even Gaia's billion-star census represents less than 0.5% of the total stellar population. The rest remain mysterious, their histories unexamined. Consider the sheer scale of what happened during the Kraken merger. Two galaxies, each containing billions of stars, collided over the course of hundreds of millions of years. This wasn't a quick event by any measure. The initial encounter would have sent gravitational ripples through both systems, disturbing stellar orbits and compressing gas clouds. As the galaxies passed through each other the first time, they didn't simply stick together. Gravitational dynamics are more complex than that. They likely passed through, separated, then fell back together again, performing a cosmic dance that might have taken multiple passages before finally settling into a merged configuration. During these passages, individual stars almost certainly never collided. Space is vast, and stars are tiny in comparison. Even in the densest parts of galaxies, the distance between stars is enormous relative to their size. If you scaled the Sun down to the size of a grain of sand, the nearest star would be about 4 miles away. So when galaxies collide, it's really the gravitational fields that interact, not the stars themselves. The stars pass through each other like two swarms of bees interpenetrating, each bee oblivious to the others, guided only by the collective gravitational pull of the swarms. But gas clouds do collide. Unlike stars, interstellar gas clouds are diffuse and can physically impact each other. When gas clouds from two galaxies slam together at hundreds of kilometers per second, they create shock fronts, regions of compressed, heated gas. This compression triggers gravitational collapse in the densest regions, initiating bursts of star formation. These starburst events can increase the rate of star formation in a galaxy by factors of 10 or even 100 compared to normal times. The Kraken merger likely triggered such a starburst in the young Milky Way. Millions or billions of new stars would have been born in a relatively short cosmic timespan, perhaps just a few 100 million years. Many of these would have been massive, hot, blue stars that burn through their fuel quickly and explode as supernovae. For a period lasting millions of years, the merger region would have been illuminated by these brilliant massive stars and punctuated by frequent supernova explosions. If any astronomers had existed elsewhere in the universe with powerful enough telescopes, they might have classified the merging Kraken Milky Way system as a starburst galaxy, remarkable for its intense luminosity and rapid star formation. Those massive stars are long gone now, having lived fast and died young. But their legacy remains. When massive stars explode, they synthesize and scatter heavy elements: carbon, oxygen, iron, gold, uranium. These elements mix into the interstellar medium and become incorporated into later generations of stars and planets. Some of the atoms in your body were almost certainly created in supernova explosions triggered by the Kraken merger. You are made not just of star stuff, but specifically of star stuff created during one of the most dramatic events in our galaxy's history. The dark matter component of this merger deserves closer examination. We know dark matter exists because galaxies rotate too fast to be held together by the gravity of their visible matter alone. There must be additional mass, about 5 times more than the visible matter, providing extra gravitational glue. This dark matter forms extended halos around galaxies, far larger than the visible galactic disks. When Kraken merged with the Milky Way, the two dark matter halos merged too. But dark matter is collisionless. It doesn't interact electromagnetically like normal matter, so it doesn't form shock fronts or lose energy through collisions. Instead, the dark matter particles from both galaxies simply pass through each other, redistributing themselves according to gravitational dynamics. Some fraction of Kraken's dark matter settled into the merged halo. Some might have been flung into the outer reaches of the system. And some, through complex three-body gravitational interactions, might have been accelerated to such high velocities that it escaped the system entirely, flying off into intergalactic space. This has implications for dark matter detection experiments. Here on Earth, physicists are trying to detect dark matter particles directly by building ultrasensitive detectors deep underground, shielded from cosmic rays and other background radiation. These experiments assume dark matter particles are constantly streaming through the Earth as we orbit the Sun and the Sun orbits the galactic center. But the velocity distribution of these particles, how fast they're moving and in what directions, depends on the detailed structure of the dark matter halo, which in turn depends on the merger history. If Kraken contributed a significant fraction of the dark matter in our region of the galaxy, and if that dark matter has a different velocity distribution than dark matter from the original Milky Way, then detection experiments might need to account for this. Some researchers are investigating whether features in the dark matter halo structure, possibly related to ancient mergers like Kraken, might create focused streams of dark matter particles moving in coherent directions. These streams could potentially make detection easier, or at least change the expected signal in detectors. The timing of the Kraken merger, about 9 billion years ago, places it in a crucial epoch of cosmic history. The universe was only about 4.7 billion years old at that time, roughly one-third of its current age. Star formation across the universe had already peaked and was beginning its long decline. The rate at which new stars form has been decreasing steadily since about 10 billion years ago, as the universe expands and the supply of fresh gas for star formation gets depleted. Galaxy mergers like Kraken played a role in this cosmic story. Major mergers can trigger intense but brief bursts of star formation, rapidly consuming available gas. After the starburst fades, there may be less fuel left for future star formation. Additionally, the energy from supernovae and active galactic nuclei during mergers can heat gas and blow it out of galaxies entirely, further reducing the material available for making new stars. So paradoxically, the very events that trigger star formation can also contribute to its long-term decline. The Milky Way's star formation rate today is relatively modest, about 1 to 3 solar masses worth of new stars per year. That might sound like a lot, but spread across the entire galaxy, it's quite low. Most of the stars we see, probably 80 to 90%, formed more than 5 billion years ago. The galaxy had a much more active youth, and events like the Kraken merger were part of that vigorous adolescence. There's an interesting connection to the concept of galactic habitable zones. Astronomers have long discussed habitable zones around stars, the range of orbital distances where a planet could maintain liquid water on its surface. But you can also think about habitable zones within galaxies. The central regions of galaxies are hazardous: too many nearby stars, too much radiation from the central black hole, too many supernovae. The outer regions might be too metal poor, lacking sufficient heavy elements to form rocky planets. The Sun orbits in what some researchers consider the galactic habitable zone, about 26,000 light-years from the center. But the merger history affects this concept. During major mergers like Kraken, even regions normally considered safe might experience increased hazards. Stars get scattered into new orbits, potentially carrying their planets into more dangerous regions. Supernova rates increase everywhere. Gravitational perturbations might disrupt planetary systems or send comets plunging toward inner planets. Could the Kraken merger have influenced the eventual emergence of life in our galaxy? It's possible. If the merger enriched our region with heavy elements, that could have made it easier for solar systems like ours to form later. If it triggered violent conditions that made life difficult during the merger epoch, that might explain why we don't see evidence of civilizations that arose earlier than us. Perhaps they were disrupted or destroyed. Or perhaps we're overthinking it, and life is resilient enough that galactic mergers are merely background noise, barely noticed by organisms on stable planetary surfaces. The identification of specific globular clusters as belonging to Kraken is particularly valuable for understanding ancient stellar populations. Globular clusters are stellar fossils, preserving information about the conditions in which they formed. Their stars are metal-poor compared to the Sun, meaning they formed from primordial gas that hadn't been enriched much by previous generations of stars. Studying these clusters tells us about the early chemical evolution of galaxies. Different globular clusters have different chemical signatures, reflecting the specific gas clouds from which they formed. By grouping clusters with similar signatures and orbital properties, astronomers can identify which ones likely formed together in the same progenitor galaxy. This is how the Kraken-associated clusters were identified. They form a coherent family with shared characteristics that distinguish them from clusters that formed in the main Milky Way or in other merger victims. Each cluster contains hundreds of thousands of stars all packed into a sphere only tens of light-years across. For comparison, the nearest star to our Sun is over 4 light-years away. In a globular cluster's core, stars might be separated by only light weeks or light days. If any planets exist in these clusters, and it's unclear whether stable planetary orbits are possible in such crowded environments, the night sky would be spectacular. Instead of seeing a few thousand stars like we do from Earth, you might see millions of brilliant points of light, close enough that the nearest stars would appear as visible disks rather than points. The fact that these clusters survived the merger is remarkable. Tidal forces during a galactic collision are immense. The gravitational field changes rapidly as different parts of the merging galaxies exert varying pulls. Many clusters likely didn't survive. They would have been torn apart by tidal stress, their stars scattered into the galactic halo as individual field stars. The clusters we see today are the resilient ones, tightly bound enough to hold together through the gravitational chaos. Some researchers are using the surviving Kraken clusters to constrain the merger dynamics. By simulating different merger scenarios, different masses, different orbital parameters, different impact angles, and seeing which simulations produce cluster populations matching what we observe, they can narrow down exactly how the merger happened. It's like reconstructing a car accident from the debris pattern, except the accident happened 9 billion years ago and involved objects containing hundreds of billions of solar masses. The concept of multiple independent discoveries of Kraken deserves emphasis. Science works best when results can be independently verified. If only one team had claimed to find evidence for Kraken, there might be healthy skepticism. Perhaps they made an error in their analysis, or perhaps they were seeing patterns in noise. But when 4 separate teams, using different datasets, different analysis methods, and different theoretical approaches, all arrive at the same conclusion, confidence increases dramatically. This is particularly important for a claim as extraordinary as reconstructing a galaxy that ceased to exist billions of years ago. Without independent verification, it would be too easy to dismiss as speculation. But the convergence of independent lines of evidence, orbital dynamics, chemical abundances, age dating, spatial distributions, all pointing to the same ancient merger event makes the case compelling. The methodology also creates a template for finding other merger remnants. Astronomers can now apply similar techniques to search for additional ghost galaxies hiding in the Milky Way's stellar population. Each discovery adds another piece to the puzzle of galactic assembly. We're building a family tree of the Milky Way, identifying its ancestors and determining how much each contributed to the galaxy we see today. Some of these discoveries might reveal even older mergers, events that happened 10 or 11 billion years ago when the universe was very young. The signatures would be fainter, the evidence more degraded, but the potential scientific payoff is enormous. The earliest mergers shaped the fundamental structure of our galaxy, establishing the initial mass distribution and chemical enrichment that influenced everything that came after. There's also the possibility of discovering very recent mergers, events that happened only a few billion years ago. These would have less degraded signatures, making them easier to study in detail. The Sagittarius dwarf galaxy is actually in the process of merging with the Milky Way right now. It's being torn apart by tidal forces, stretched into streams of stars that wrap around the galaxy. We're witnessing a merger in progress, albeit in slow motion from our perspective. The energy released during the Kraken merger was staggering. When galaxies collide, gravitational potential energy converts into kinetic energy as stars accelerate into new orbits. Some of this energy goes into heating the gas, some into radiation, and some remains as kinetic energy in the stellar motions. The total energy involved in a major merger like Kraken exceeds anything we can easily conceptualize, more than all the supernovae that have ever exploded in human history combined, and sustained over hundreds of millions of years. Yet despite this incredible violence on large scales, the actual experience for any hypothetical planets in the system might have been surprisingly mild. A planet orbiting a star in either galaxy would barely notice the merger directly. Stars don't collide, remember, the distances are too vast. From the planet's surface, you might notice the sky gradually filling with more and more stars as the two galaxies interpenetrated. Over millions of years, familiar constellations would shift and change as your star's orbit evolved. There might be an increased rate of supernovae visible in the sky as the starburst progressed. But day-to-day life on the planet would continue largely undisturbed. The real dangers would be more subtle and long-term. Gravitational perturbations might disturb the planet's orbital stability over millions of years. A close passage by another star could destabilize the planetary system, ejecting planets or sending them into eccentric orbits. The increased supernova rate might periodically bathe the planet in harmful radiation. But these would be gradual changes, nothing like the catastrophic collision you might imagine when you hear, two galaxies crashed into each other. This illustrates an important principle in astronomy: scales matter enormously. Events that are violent and dramatic on galactic scales might be barely perceptible on stellar or planetary scales. Conversely, events that are catastrophic for individual planets, asteroid impacts, nearby supernovae, stellar flares, might be utterly negligible in terms of galactic evolution. The role of supermassive black holes in mergers is an active research area. We know the Milky Way has a supermassive black hole called Sagittarius A at its center, with a mass about 4 million times that of the Sun. Kraken, being a substantial galaxy, almost certainly had its own central black hole, possibly comparable in mass. When two supermassive black holes come together in a merger, they don't immediately combine. Instead, they sink toward the center of the merged galaxy through a process called dynamical friction. As the black hole moves through the stellar environment, gravitational interactions with nearby stars sap its orbital energy, causing it to gradually spiral inward. This process can take hundreds of millions to billions of years. Eventually, the two black holes get close enough that they form a binary system, orbiting each other. At this stage, they're still separated by light years, but they're gravitationally bound. The binary then needs to shrink further before the black holes can merge. This is the final parsec problem, getting the binary from a separation of about 1 parsec, 3.26 light-years, down to the tiny distances where gravitational wave emission becomes efficient enough to drive the final merger. Several mechanisms might solve this problem. Interactions with stars passing through the binary system can carry away energy and angular momentum. Gas flowing into the central region can create drag forces. And gravitational wave emission, while weak at large separations, becomes increasingly important as the binary shrinks. Eventually, when the black holes are separated by only a few times their event horizons, gravitational waves become the dominant mechanism, causing them to spiral together rapidly and merge in a spectacular burst of gravitational radiation. The merger of supermassive black holes from the Kraken event probably happened sometime after the galactic merger itself. Possibly hundreds of millions of years later. The gravitational waves from this merger would have been incredibly powerful, briefly outshining in gravitational wave luminosity all the stars in the observable universe combined. These waves propagated outward at the speed of light, stretching and squeezing space itself as they passed. Those gravitational waves passed through Earth's location about 9 billion years ago, long before the solar system existed. They're gone now, racing outward into the expanding universe. But future gravitational wave detectors might observe similar events happening in distant galaxies, giving us real-time observations of supermassive black hole mergers and allowing us to study these processes directly rather than reconstructing them from ancient evidence. The aftermath of such a merger is fascinating. The combined black hole would be more massive than either progenitor, but not quite as massive as their sum. Some mass gets converted to energy in gravitational waves, according to Einstein's E = mc squared. The merged black hole might receive a kick from asymmetric gravitational wave emission, potentially displacing it from the galactic center. In extreme cases, these kicks could be strong enough to eject the black hole from the galaxy entirely, creating a wandering supermassive black hole in intergalactic space. Is Kraken's black hole still wandering somewhere in the Milky Way's halo, or did it merge with the progenitor of Sagittarius A-? We don't know for certain. Searching for wandering supermassive black holes is challenging because black holes don't emit light themselves, they're only visible through their gravitational effects on surrounding matter. If a wandering black hole has no nearby gas or stars, it might be essentially invisible, a massive dark object lurking unseen. However, there are search strategies. A wandering black hole would gravitationally lens light from background stars and galaxies, creating characteristic distortion patterns. It might have a retinue of stars bound to it, forming a compact cluster moving through the galaxy with unusual kinematics. And if it passes through a gas cloud, it would heat and ionize the gas, potentially creating observable emissions. Surveys are actively searching for these signatures. The chemical evolution story tied to Kraken is intricate. When the universe emerged from the Big Bang, it consisted almost entirely of hydrogen and helium, with trace amounts of lithium. Every heavier element, what astronomers call metals, had to be created inside stars. The first generation of stars, called population 3 stars, formed from this pristine primordial gas. They're thought to have been extremely massive, hundreds of times the Sun's mass, and they lived brief lives before exploding as supernovae or collapsing into black holes. These first supernovae seeded the universe with the first heavy elements. Subsequent generations of stars formed from gas enriched by these elements, and each generation continued the process of creating and distributing heavier elements. By the time Kraken formed, the universe was already several billion years old, and multiple generations of stars had lived and died. The gas from which Kraken stars formed had been enriched to some level, though still far more metal-poor than the Sun. When Kraken merged with the Milky Way, it brought its own chemical enrichment history. The stars that formed in Kraken did so from gas with a particular chemical composition, reflecting the specific history of star formation and supernova explosions in that galaxy. This composition differs subtly from stars that formed in the main Milky Way progenitor. By measuring these subtle differences, ratios of various elements like iron, magnesium, calcium, and europium, astronomers can chemically tag stars according to their origin. It's like using DNA analysis to determine someone's ancestry, except we're using chemical abundances to determine a star's ancestral galaxy. Stars that show the characteristic Kraken chemical signature are identified as having formed in that galaxy, even though the galaxy itself no longer exists. This chemical archaeology is one of the most powerful tools for reconstructing merger histories. Different types of supernovae produce different element ratios, which adds another layer of information. Core-collapse supernovae, which result from massive stars, produce relatively more oxygen and magnesium. Type Ia supernovae, which result from exploding white dwarfs in binary systems, produce relatively more iron and nickel. The ratio of these element groups in a star's atmosphere tells you about the balance of supernova types that enriched the gas from which it formed. If Kraken had a different star formation history than the Milky Way, perhaps forming stars more rapidly in bursts rather than at a steady rate, the ratio of core collapse to type Ia supernovae might differ, leading to observable differences in element ratios. These differences persist billions of years after the galaxy was destroyed, encoded in the atmospheres of its surviving stars. The study of Kraken also informs our understanding of galaxy populations in the early universe. Kraken was likely similar to galaxies we observe at high redshifts, galaxies so distant that their light has taken most of the age of the universe to reach us. These distant galaxies appear as they were billions of years ago, during the same epoch when Kraken existed as an independent galaxy. By studying Kraken's remnants in detail, we can learn about the properties of typical galaxies from that era, their masses, star formation rates, chemical compositions, structures. This complements observations of distant galaxies, where we can see what they looked like but can't study individual stars or detailed internal structures. Kraken gives us a close-up view of what those distant galaxies were like, even though we're seeing it billions of years after its destruction. There's an irony here. We can study Kraken's stellar population star by star, measuring individual stellar properties with high precision, precisely because it was destroyed and its stars are now scattered throughout the Milky Way where we can observe them easily. If Kraken still existed as an independent galaxy billions of light-years away, we could barely resolve its overall shape and would have no hope of studying individual stars. Sometimes destruction grants a different kind of immortality, through detailed forensic examination. The educational implications of discoveries like Kraken are significant. For centuries, we taught that the Milky Way was simply our galaxy, a static structure we happen to inhabit. Now we understand it as a dynamic, evolving system with a complex history of assembly and growth. This changes how we think about our place in the cosmos. We're not living in an eternal, unchanging structure. We're living in a galaxy that was built through the violent consumption of smaller galaxies, that will itself be consumed in the future collision with Andromeda, and that is part of an even larger structure, the local group, that will eventually merge into a single massive galaxy as the universe ages. Everything is temporary, everything is dynamic, everything has a history and a future. This perspective is humbling but also exhilarating. We exist at a particular moment in cosmic evolution, in a galaxy with a particular history, orbiting a particular star that formed from material enriched by countless previous generations of stars, some of which formed in galaxies that no longer exist. The atoms in our bodies have journeyed through space and time, cycling through stars and galaxies across billions of years, before temporarily assembling into the complex patterns that constitute living things. And we're conscious. We can figure this out. We can reconstruct events that happened before our planet existed using careful observation, mathematical analysis, and computational simulation. We can read the cosmic fossil record and piece together a coherent history. This capability, the ability to understand our cosmic context, is perhaps one of the most remarkable features of human intelligence. The practical applications of this research extend beyond pure scientific curiosity. Understanding galaxy mergers helps us interpret observations of distant galaxies and improves our cosmological models. The techniques developed for galactic archaeology have applications in other areas of astronomy. The computational methods used to simulate mergers advance our capabilities in scientific computing generally. And the fundamental physics involved, gravity, stellar evolution, nuclear synthesis, underlies many other phenomena we want to understand. There's also an inspirational dimension. Young people learning about discoveries like Kraken might be motivated to pursue careers in science, technology, engineering, or mathematics. The narrative of cosmic history, the building of galaxies through mergers, the cycling of matter through stars, the evolution of structure from the Big Bang to the present, provides a grand context for understanding our place in nature. The ongoing saga of the Milky Way's merger history will continue to unfold as new data arrives and new analysis techniques develop. Each discovered merger remnant adds detail to the picture. Kraken is currently the largest known victim, but that could change. Perhaps a future survey will identify evidence of an even more massive merger from earlier times. Or perhaps we'll discover that some of what we attribute to Kraken actually comes from multiple separate mergers that happened at similar times, making the story even more complex. The interplay between observation and simulation continues to drive progress. Simulations predict what mergers should look like in terms of observable properties. Observations test these predictions and sometimes reveal unexpected features. When observations disagree with simulations, both observers and theorists sharpen their tools and deepen their understanding. Sometimes the discrepancies reveal flaws in the simulations, missing physics, incorrect assumptions, insufficient resolution. Other times the observations were misinterpreted or the data was contaminated by systematic errors. And sometimes both sides are partially right, and the truth lies in a more nuanced understanding that incorporates insights from both approaches. This dialectic between theory and observation is the engine of scientific progress. The Kraken discovery also highlights how much modern astronomy depends on large surveys and big data. The datasets from Gaia contain measurements of over 1 billion stars. Spectroscopic surveys provide detailed chemical information on millions of stars. Processing and analyzing this data requires sophisticated computational infrastructure and algorithms. No individual researcher can examine 1 billion stars personally. We need automated pipelines, machine learning algorithms, and collaborative databases. This represents a shift in how astronomy operates. The era of the lone astronomer at a telescope, making discoveries through individual observations, still exists but is increasingly supplemented by large collaborative efforts involving hundreds of scientists working with massive datasets. The discovery of Kraken exemplifies this modern approach. Many people contributed to building the datasets, developing the analysis tools, running the simulations, and interpreting the results. Yet there's still room for individual insight and creativity. Someone had to have the idea that ancient mergers might be detectable through chemical and dynamical signatures. Someone had to design the analysis that could separate Kraken's remnants from the general stellar population. Someone had to recognize the patterns in the data that indicated a massive ancient merger. Big data doesn't interpret itself. It still requires human intelligence, creativity, and insight to extract meaning. The future of this field looks bright. Next-generation surveys will measure billions more stars with even greater precision. New theoretical models will incorporate more detailed physics. Improved computational power will allow higher-resolution simulations. The combination should reveal the Milky Way's merger history in increasingly fine detail, perhaps even allowing us to reconstruct individual merger events with precision, knowing not just that they happened, but exactly when, how, and what consequences they had for the galaxy's evolution. The story of Kraken reminds us that the universe has a memory, encoded not in books or digital storage, but in the positions and properties of stars scattered across hundreds of thousands of light-years. Every star is an archive. Every chemical abundance is a clue. Every orbital pattern tells a story about events that shaped the cosmos long before humans existed to wonder about them. We live in a galaxy built from the wreckage of others. The stars above us are survivors and immigrants, refugees from cosmic catastrophes that destroyed their home galaxies billions of years ago. Some of the atoms in your body were forged in stars that belonged to Kraken, released in supernova explosions during the merger, mixed into gas clouds, and eventually incorporated into the molecular cloud that collapsed to form our solar system. You are made of dead galaxies. You are the universe examining itself, using tools fashioned from transformed stardust to decode messages written in stellar orbits across billions of years. The Kraken may be gone, devoured and scattered, but it persists, in the stars that once belonged to it, in the elements it contributed to the cosmic mix, and now in our understanding of how galaxies grow and evolve. And this process continues. The Milky Way is still consuming smaller galaxies. In 4 billion years, we'll collide with Andromeda in an even more spectacular merger. Future astronomers in that distant era might study the scattered remnants of our Milky Way the same way we study Kraken today, piecing together our story from the fossils we leave behind. The cosmos is not static. It's a dynamic, evolving arena where structure builds through violence, where destruction and creation are intertwined, and where patient observation can reveal secrets hidden for eons. Kraken's discovery is one chapter in this ongoing story of cosmic archaeology, a ghost galaxy found through mathematics and light, giving us a glimpse into our galaxy's turbulent past and reminding us that even in the vastness of space and time, nothing is truly lost. The evidence remains, waiting for those curious enough to search for it and clever enough to read the signs. The universe keeps its records. We're learning to read them.